Hey everyone, today we're going to talk about simple harmonic motion. We're going to talk about what it is, how to come up with our kinematics equations like we've been doing to figure out the velocity of an object to experience this type of motion, its acceleration at some point, and its position. So if we look at this GIF and think about when we talked about springs, we have a force from a spring that's dependent on its position. Previously we found that our spring force is equal to the negative kx, k being our spring constant and x being the displacement from equilibrium. So in this GIF, if we that time axis, the x-axis, if we treat that as our equilibrium, this mass, after we pull it down, since it has some force dependent on its position with the spring from equilibrium, it's going to have an acceleration that varies. And so we could figure this out just by starting off by coming up with a couple simple relations. So as you see here in the top, it talks about a time domain, and in the bottom it's representing a space domain. It's measuring the length of the wave, the physical length of the wave, and in the top it's measuring how long it takes to go through one cycle. This object goes full down and then full back up and then back down to the position, and how long that takes. So in the video today we're going to be focusing on the time domain, and then the next video we'll talk more about the space domain. So we could represent this motion as a sinusoidal wave because we're just moving up and down, right? It's a repeating wave. I have it drawn where our time equals 0, that we're at the origin. A lot of times you'll see it where it's drawn at its max amplitude initially, because you could think of a mass on a spring. You pull it out and initially it's out at the max amplitude and you let it go and it's set into motion. How I've drawn this is the object's already in motion, and we're going to look at it from there, and we'll work at an example where we actually assume that at time equals 0 that we're at our max amplitude, but we'll see all that. So there's a few things that we need to take away from this graph. One, because we're going to assume that our motion isn't being dampened, we're going to have the same amplitude as this spring. Starting at equilibrium, it's going to go up to some max amplitude 2 at this point 2, and I have this drawn just to kind of mirror the graph what's actually happening. We're measuring the displacement, so at point 2 we're at our max amplitude. Point 3 we come back down, we're back at equilibrium position. This brown line is the equilibrium position, and then at point 4 we're down at our negative amplitude, and 5 we're back at equilibrium. So this would be one full cycle. We went up, we came back down, and then we started back over, and this cycle would go on and on. So the time it takes to complete one cycle is known as our period, the time for one rotation. And so that concept will come in handy, as well as the fact that our period t is equal to 1 over our frequency, which should make sense, because if big T is the time it takes to complete one cycle, if we take the inverse, it's going to tell us how many cycles are in a second, 1 second, which would be measured in hertz, cycles per second. So let's think about how we could come up with an equation, a kinematic equation, just representing the position versus time. Well, this is a sinusoidal wave, so we know we could use a trig function to describe this pretty easily. And the amplitude of it is just going to be dependent on how far it's displaced. So what we could say is that our position with respect to time is equal to our amplitude, our total, our greatest magnitude displaced from the equilibrium. And here I'm using sine as our function since we're starting at the origin. That isn't always the case, but we could have had some shift, but let's not worry about that. We'll see in the next problem that we're not always picking sine. So this isn't always going to be the way to solve this, but in the end, it doesn't really matter what you choose as long as you plug everything in correctly. So we got the amplitude times the sine of our, well, we know this is time dependent, so we have time in here, but we're multiplying it by something here. We don't know what that is, but let's think about what we want. We want, after time has elapsed one period, we want our sine function to reset. So, and we're working in radians, so it's going to be in terms of 2 pi radians. So what we could do is, if we replace our our question mark rather with our period in the denominator, we know that when our time is equal to our period, that will have gone 2 pi radians, which is 1 cycle. So this is a scaling factor that just would make our make sure that depending on our period, how long our period is how long or how often we will cycle through our position from our full cycle of our position. But we don't know what our period is. We're not told what it is, but maybe we could come up with a relationship to figure that out. So what this is known as, this term, this 2 pi over our period, is known as angular frequency. And this is the Greek lowercase letter omega. And so instead of writing 2 pi over our period, we could just replace that with omega. And so for those of you that are in calculus now, I'm not sure if you guys have done the derivatives and integration of trig functions. This is pretty much the only other thing in the class that you'll need to learn, if you aren't already aware, but is how to take the derivative and the integral of trig functions. And so we'll just be mostly working with sine and cosine. We'll work with tangent sometimes, but we could generally replace that in all the examples I can think of off the top of my head. But anyways, so our position function with respect to time now becomes a sine omega t. And so at t equals 0, sine's going to be 0. We're at position 0, so that's good. And then as we go through, we get to our 1/4 of our period will be at our max amplitude, because at that point sine of omega t will equal 1, so we'll just have our amplitude. And then so on and so forth, and this will just keep cycling through. So when we take the derivative of sine, we're going to end up with cosine. So that should be pretty apparent, because when we look at sine, we're coming up positive. We have a positive slope. So when we take the derivative of that, we're going to have a positive value, which is going to be our cosine function. If you could think of our cosine function starting up at our amplitude and dropping down, it would be our derivative of sine, because we're starting at our slope is equal to 1, or is equal to our amplitude. And then we're coming down with our cosine function to 0, which would meet right here where our slope is 0 from sine, and so on and so forth. So what we get is, when we take the derivative of our position with respect to time, we end up with the derivative. We got to use the chain rule when we take the derivative of this, where we take the derivative of the inside multiplied by the derivative of the outside. So when we take the derivative of the inside, we're taking it with respect to time. So we end up with just omega. So we're going to multiply omega by the derivative of the outside. Well, the first term, a, is not dependent on time, so we don't have to worry about that. But sine is. So the derivative of sine is just going to be cosine, as I mentioned previously. And we end up with a omega cosine of omega t. Well, we're trying to get to figure out what omega is, solve for that, which isn't helpful yet, and you'll see why shortly. But if we take the derivative of this, we're going to end up with our acceleration with respect to time. which will be helpful because we know how to calculate the force of a spring, right? So we should know how to calculate acceleration using Newton's second law. Oh boy. Sorry about that. Okay, so we end up with our acceleration with respect to time is our negative, our amplitude omega squared sine of omega t. And that's because when we took the derivative of our velocity with respect to time, the derivative in the inside is our omega once again. So we're multiplying the outside by that. So we get our omega squared, and then our derivative of the outside is only going to be dependent on our cosine, is the only thing that is time dependency, which is going to become a negative sine. So the important thing is to remember, if this is new to you, the derivative of sine is going to be a positive cosine. The derivative of cosine is a negative sine. And then, of course, when we integrate, that is backwards. Okay, so what can we do with this acceleration? Let's take a look at how this compares to, this equation compares to if we solved for acceleration using our force formula. Okay, so all I did was copy this equation over from that last page, our acceleration with respect to time that we found. And for a spring, we know that our force is equal to negative kx. Sorry, I keep hitting the wrong button. Okay, so if we know our force is negative kx, using Newton's second law, F equals ma, or acceleration equals our force divided by our mass, we see that we have an acceleration of negative kx over m. Well, this acceleration has got to be equal to this acceleration, right? At some point when our amplitude and x are the same, they're going to have the same value. So we could set those two equations equal to each other, where we have the acceleration that we found from solving from the force of a spring. The restoring force of a spring is equal to the negative kx over m. And then I just copied, once again, the equation that we came up with, taking the derivative of the second derivative of position versus time. So when we're at some time where where sine of theta equals 1 rather, our x position and our a position is going to be the same, because when sine of omega t equals 1, we're at our max amplitude. Because if you think back to our position versus time equation, it would have been just 1 times our amplitude, which makes sense because we're at our max amplitude. So if we apply this relationship where x and a are equal to each other when sine of omega t equals 1, well, we get rid of our sine function because it just becomes a 1, and we also cancel our x and our a out because they're equal to each other. And what we're left with is k over m equals omega squared. And so, solving for omega, we see that our angular frequency for a mass on a spring is equal to the square root of k over m. And once again, our k is our spring constant, and m is the mass that's being oscillated. Which should make sense, because the stronger our spring, the faster it's going to be able to move an object. But a heavier object's harder to move, so the greater that is, it's going to reduce our angular frequency. So plugging this in with, or looking at this, our omega, what we saw before, was 2 pi over t. And so I'm just substituting that in, what we originally had put in for our position with respect to time. And we're not changing the right side of this equation. So if we solve for our period now, we see that our period for a mass on a spring is equal to 2 pi square root of m over k. So this will be true only for a mass on a spring, which should make sense since it's dependent on the spring constant. Okay, and then the frequency, of course, is just the inverse. So all we did was flip everything over, and we get 1 over 2 pi square root of k over m. So if we look at our formula sheet on the right side, it says periodic motion. We see that we have these relations listed. So you don't necessarily need to remember them. You just need to know when to apply them. Our frequency equals 1 over our period. We got our angular frequency equals 2 pi f. And so far we've talked about, for some reason under mechanical waves is where I put the angular frequency of a mass on a spring down there right above the word fluids in the bottom right. Okay, so let's take a look at an example of this to try to make it a little more concrete. Okay, so what if we had a mass, it's hanging from a spring that's attached to the ceiling. The spring has a constant of 300 newtons per meter. And initially, we're at equilibrium, and what's going to happen is we're going to pull this box down and displace it. This is a letter A for our amplitude, but we're going to displace it 1.5 meters from equilibrium. And we want to know what our velocity of the box is going to be at 2 seconds. Well, from our previous slides, we saw that our position with respect to time is equal to, well, before, like I mentioned, we had a positive sine omega t is what we used in our or when we were talking about coming up with this equation. But in this problem, as you can see, we've displaced this object in the negative amplitude. So I put a negative out here, and we're out at our amplitude. And so since at time equals 0, we're at our max amplitude, I'm using a cosine trig function because when t equals 0, our cosine function will equal 1, and we'll be out at our negative amplitude, which should make sense because that's where we're starting in this problem. So we know if we take the derivative of this, we'll have our velocity with respect to time, right? So we just end up with, once again, the derivative of cosine is negative sine. Our negatives will cancel, and we're left with sine. And then we got to multiply by the derivative of the inside, which just becomes omega. The derivative of the term inside just becomes omega, and we multiply the outside by that. So now we have an equation that represents our velocity with respect to time. So if we substitute our relationship that we found, that our angular frequency is the square root of k over m, we know what our mass is, we know what k is, we'll end up with our velocity with respect to time looking like this. And so we know our amplitude, we know k, we know m, and we can just plug all these in. We had an amplitude of 1.5 meters, spring constant of 300, and the mass was 5. And inside of the trig function, we need to multiply by 2 seconds. That's supposed to be a 0. Okay, so we plug this in our calculator, and it turns out that our object is traveling at 3.1 meters per second at 2 seconds. Well, what if we were asked about how much potential energy the spring still has? We could easily tell how much kinetic energy it has, right? 1/2 mass times velocity squared. We know the velocity. We're given the mass from the get-go, so that's no problem. But for our potential energy, what we could do is set up an equation for the total energy, which our total energy comes from when we first pulled that mass down. We pulled it out to some amplitude. And so it was a negative amplitude, but we're squaring it, so it doesn't matter. And we know the energy, potential energy from a spring we saw before is equal to 1/2 K. In our formula sheet, it would be 1/2 Kx squared. But for our total energy, we want the energy, the total potential energy when we had no motion, and that our box was displaced, our max amplitude from equilibrium. So this is the total energy of the system initially. And then as the box starts moving, because it's going to be accelerated, it's getting that restoring force applied to it from the spring. So our kinetic energy is going to be 1/2 mv squared. And then we also still have some potential energy, because initially we have it all stored in potential energy. By the time we get to equilibrium, we no longer have potential energy. We just have all kinetic energy. And so as this box oscillates back and forth, up and down, we're going from our total potential energy, total kinetic energy, and back to potential energy as it goes up and down. So in between our equilibrium and max amplitude, we have some combination of potential and kinetic energy. So we could represent our this equation by the plugging in the velocity that we already found using kinematics, and then we could just solve for our potential energy, this term, to answer the question, because we know if we take our total kinetic energy and subtract our total energy and subtract our kinetic energy, we're left with whatever potential energy is still in the spring. So all we had to do is subtract our kinetic energy over, and I rewrote our potential energy just as PE. And then of course we know all these values. We know our max amplitude. This looks like an X, but that's supposed to be an A. And we know our velocity, and we're told our mass and our spring constant. So we could plug all this in, and we end up with 313 joules. Okay, so that's looking at a mass on a spring. What about a mass on, let's say, something like a pendulum, where we have a mass on a rope that's swinging back and forth? Because here we saw that our angular frequency equals the square root of K over M. Well, a mass for a pendulum doesn't have a spring constant. It doesn't have a spring at all. It's just a mass hanging from a rope. So let's try doing the same thing for a pendulum and see if we could come up with what our angular frequency for that would be. Okay, so what I have drawn here is pretend we have, this is attached to the ceiling, and we have a rope attached to some mass. So this is just a simple pendulum, and it's going to be displaced from equilibrium angle theta. And what our goal is to figure out, like we did for the mass on a spring, our kinematics equations, and come up with that angular frequency. So we need to look at what forces we have. Well, the mass always has our force from gravity, our weight, mass times gravity, pointing straight down. And then there's this restoring force that's trying to restore the mass back to equilibrium. It wants to be sitting here at its lowest potential or lowest energy, sitting here at equilibrium. So this force of gravity is pushing the object, or not the force of gravity, the restoring force is trying to get this object back to equilibrium. So what we have is that the tangent of theta is equal to our restoring force divided by our weight, mass times gravity. It's just our opposite over our adjacent. And so what I didn't mention is that this angle here is the same as this angle here. Is how I came up with the tangent of theta. Okay, so anyways, solving for our restoring force, because we were trying to get to some acceleration, so we could compare that like we did last time with our kinematics equations. So solve for our restoring force is just mg tan of theta. And a trick that physicists like to use a lot to get rid of angular dependency in situation is small angle approximations. So what we could do for small angles is say that the tangent of theta is equal to theta itself. And there's also another small angle approximation that the sine of theta equals the theta itself. So if this was sine, for some reason, I can't think off the top of my head a problem, but it comes up a lot in physics, where if you have tangent or sine and you're working with small angles with a pendulum, we're going to, because to make it a little easier, we need to have differential equations in class to solve the problem otherwise. So for this class, this approximation comes in handy. Anyway, so we plug that in and we have our restoring force as just mg theta. And then of course, using Newton's second law, our acceleration is just our force divided by our mass. So our acceleration is going to be equal to negative g theta. And the negative just comes from because it's trying to force the object the opposite direction than as it's been displaced. And then we also know the relationship, since we're talking about angles here, we know that the angular acceleration is equal to our translational acceleration divided by its radius, which in this case, our radius is the length of the rope or whatever is holding this mass up, L. So we could replace that, substitute our or not substitute, but anyways, get our angular acceleration just by dividing our acceleration by L. Okay, that's good, but doesn't really help us solve what our angular frequency is. So what we need to do is go back through those same steps that we did before, where we have our, and this time we're going to use angular kinematics instead of our translational kinematics, since we're moving in a circular motion in this case, unlike the spring problem. So all this is saying is basically the same thing we did before. We're starting off at some angle theta at time t, and we know we're at that angle when t equals 0. So when t is 0, cosine becomes 1, and we're at our initial angle, which should make sense. And so we take the derivative twice. Our first derivative gives us our angular velocity, which isn't helpful here. And then we take the second derivative again, and we get our angular acceleration. And so, as we saw before, the derivative of cosine is negative sine. The derivative of sine is cosine, and then we needed to multiply each time by the derivative of the inside. So when we took the derivative of the inside here, we got this omega that got pulled out, and then we did it again for the second derivative. So we're now have a representation that we solved using for our angular acceleration using our forces equations, and we solved one for our acceleration using kinematic equations. So we know that when time equals 0, that these two are going to be equal to each other, or they're going to be equal to each other, but at time equals 0 rather, and also which would be when cosine equals 1, because when inside the trig function 0, cosine becomes 1. We know that our angle theta that we're at is going to be equal to our original angle, our initial angle rather. I think I said that right. So basically this theta and this theta are going to be the same, which is going to allow them to cancel. and we're making cosine omega t equal to 1. We did that just like we did in the previous when we solved for the mass on the spring. So anyways, what we end up with, we cancel, our cosine becomes 1, our thetas are canceling each other, and what we're left with on the left side is a negative g over L, and on the right side a negative omega squared. So our negatives will cancel, and we're just going to take the square root of our both sides so we could solve for our angular frequency. So our angular frequency ended up being, for a mass on a pendulum, simple pendulum, we get the square root of g over L. And if we look at our formula sheet, this one is under periodic motion. It says omega, and it's got a subscript p there. Okay, so hopefully using these two so hopefully going through these two kind of clear up how you would solve a problem when we don't have a constant acceleration, when we have something that's constantly changing, because our force from our spring changes with our position, and our restoring force of a pendulum changes depending on our angle that we have. So we'll work some more problems and start talking about moving waves instead of just waves that are dependent on time. It's going to be dependent on time and position, we'll see. But it doesn't really complicate too much more. So if once again, under the periodic motion section of the formula sheet, you'll see that the generic position with respect to time equation I wrote here, I have two of these added together. Really, it should just go off to infinity, because we could use the superposition principle and come up with one equation for if we had several waves, let's say a double mass spring system. And so I have it written with the sine and cosine. So don't let that intimidate you, because really it's usually you're only going to need one of them in these problems. And then the phi that you see within the trig functions just are offset. So let's say in our first problem, we wanted to use cosine instead of sine. Here, let me pull that up real quick. So if we look at our first example, we used a sine function to solve for our position versus time. But what we could have done was used a cosine and added a phase. We could have used cosine and then added, instead of just having our a sine omega t, it would be a cosine omega t plus pi over 2, because we would have that quarter phase shift in order to make this still 0. Because when time equals 0, if we add pi over 2 and this was cosine, then we would still have our function equal to 0, which in this problem it was. All right, anyways, there'll be more soon about, like I said, waves that are in motion. If you guys have any questions about this, let me know, and I'll be opening up the homework shortly. Take care.